The investigation into the universe's beginning and ongoing development is now at a crucial point in cosmology. Dealing with some of its most fundamental ambiguities is the primary focus, particularly determining how quickly the universe has expanded over the past 10 years. There are two main ways to measure this expansion, and the results have led to contradictions. The most recent observations of the universe's current state indicate that the rate of growth, known as the Hubble constant, is approximately 9% higher than predictions derived from data from the early universe. Researchers had hoped that the James Webb Space Telescope, JWST, the most advanced telescope ever developed, would offer a definitive solution to this problem. But the new information from JWST has only served to widen the gap. This has led to inquiries regarding the accuracy of the established model of the universe and sparked heated discussions within the scientific community concerning whether these changes necessitate new physics or completely replace the existing theories that have been valid for decades. This possibility is both exciting and unsettling, as it suggests we may be overlooking an essential component of the universe that could dramatically alter our comprehension of its past. The past of the universe traces back to the Big Bang, a massive explosion that generated matter and energy instantaneously. The universe began as a space filled with extremely hot and dense plasma made up of particles of matter and antimatter. These particles collided and destroyed one another, but scientists believe a subtle imbalance permitted a slight excess of matter over antimatter, thereby preventing the universe from annihilating itself. The plasma was then compressed by gravity, heating it to the point where sound waves, called baryon acoustic oscillations, moved through it at speeds greater than half the speed of light. The high energy density of the early universe pushed some matter far enough to survive the intense heat. As the universe ballooned in size, regular matter is thought to have begun forming groups. Eventually, invisible dark matter would form the first galaxies. These galaxies are thought to be connected by a vast cosmic web of dark matter and energy. As the universe developed, this amplified the energy density, and the rate of expansion gradually slowed. But around 5 billion years ago, galaxies began to recede from each other at an accelerated speed, driven by a cryptic force known as dark energy. The most commonly accepted explanation is that dark energy functions as a constant force woven into space-time itself, embedded in the fabric of the universe's expansion. This force, known as lambda in Einstein's theory of general relativity, retains the same density even as the universe expands. As the density of ordinary matter decreases over time, dark energy took over as the driving force behind the expansion of the universe. Together with dark matter and regular matter, these forces form the lambda cold dark matter, lambda CDM model, which describes the universe's evolution and its eventual fate, a predicted heat death, also referred to as the Big Freeze. While many of the model's predictions have been confirmed, the nature of dark energy and dark matter remains one of the most significant unresolved challenges facing cosmologists. A central issue is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate result in inconsistent outcomes. This discrepancy is so pronounced that it has become one of the field's most urgent problems. Observations from the early universe suggest a slower expansion rate than the lambda CDM model anticipates, but these early measurements have been rigorously tested and validated through various observations. According to Nobel laureate astrophysicist Adam Rees, who led the team responsible for the most recent JWST measurements, a plausible justification for the gap is that our current model is missing something crucial. Measuring the expansion rate of the universe requires more than simple observation. One of the primary methods includes examining the cosmic microwave background, CMB, which is the universe's first light emitted roughly 380,000 years after the Big Bang. This imprint can be seen across the sky and was extensively mapped between 2009 and 2013 by the Planck satellite of the European Space Agency. The CMB provides a detailed view of the early universe. Though the temperature variations are small, they mark areas of higher or lower matter density. These variations reflect the acoustic oscillations that help cosmologists calculate the Hubble constant, yielding an estimate of roughly 67 kilometers per second per megaparsec. To clarify, this means that a galaxy 1 megaparsec away would recede at 67 kilometers per second. A galaxy 20 megaparsecs away would recede at 1,340 kilometers per second. A galaxy 62.3 megaparsecs away would recede faster than the speed of light, according to this model. Another method involves studying variables like pulsating stars, whose outer layers expand and contract consistently as they release and absorb radiation. Astronomer Henrietta Swan Leavitt discovered this behavior in 1912. It allows astronomers to measure a star's total luminosity, which can be used to estimate its distance. The Cepheid variable method, part of what's known as the cosmic distance ladder, is a key tool for measuring vast distances across the universe. Measuring is required for each step on this ladder, first by confirming nearby Cepheids' distances, then using that data to measure stars and supernovas farther away. In 2019, Rees and his team used this method to study the closest Milky Way neighbor, the Large Magellanic Cloud. Their results were startling, showing a significantly higher rate of expansion at 74 kilometers per second per megaparsec. During this time, the Hubble Space Telescope played a crucial role. However, its accuracy was limited in crowded regions of space, causing distant Cepheids to blend in with nearby stars. Some cosmologists suggested that this measurement error may have caused the discrepancy. In December 2021, the James Webb Space Telescope launched with the hope of resolving this issue. With its 6.5-meter wide mirror, nearly 3 times larger than Hubble's, and superior infrared capabilities, JWST can detect fainter objects and observe across a wider spectrum. Comparing Cepheids in galaxy NGC 4258 to supernovas, JWST revealed results nearly identical to Rees's previous findings, with an average expansion rate of 73 kilometers per second per MPC. Other measures, including those by Wendy Friedman using the Hubble telescope and gravitational lensing, returned similar speeds of 66.6 and 69.6 kilometers per second per MPC. These findings caused a stir in the cosmological community. As noted by Ronnie Keese, a cosmologist from the University of California, even a small difference of 7 kilometers per second is extremely unlikely to be an error, especially in light of the measurement's accuracy. This has led to a division among cosmologists, with some pointing to measurement errors, and others suggesting that new physics are required, or perhaps a combination of both. According to Keese, the majority of the data points to the need for new physics. One leading hypothesis involves dark energy's changing behavior. If dark energy was once stronger and has gradually weakened, it could explain why the early universe appeared smaller and expanded faster. Other theories propose the existence of 2 types of dark energy, or interactions between dark matter and light. But these ideas face significant challenges. The idea that dark energy's properties might evolve over time adds complexity to cosmological models. If dark energy has been changing, it implies the universe's expansion history is not as straightforward as once believed. This introduces the possibility that our foundational assumptions, based on the lambda-CDM model, might need revision or expansion. Some cosmologists have proposed exotic alternatives. Perhaps there are interactions between dark matter and dark energy, or additional fundamental particles and fields yet to be discovered. There's also the possibility of modifying general relativity itself, Einstein's century-old theory, which underpins much of modern cosmology. Though radical, such ideas are gaining traction in light of persistent observational tensions. Meanwhile, JWST continues to provide unprecedented detail about the early universe. It has captured images of proto-galaxies and star clusters that seem to contradict conventional timelines. Some of these galaxies appear too massive, structured, and chemically mature to have formed so soon after the Big Bang. Their very existence challenges existing simulations and cosmological expectations. In addition, JWST's deep field observations are helping researchers investigate reionization, the era when the first stars and galaxies reionized the neutral hydrogen in the early universe. This process shaped the large-scale structure of the cosmos, and understanding its timing and mechanisms is crucial for building accurate models of cosmic evolution. As new data pours in, scientists are also improving precision tools to further test cosmological models. These include more refined measurements of type Ia supernovae, better calibration of Cepheid variables, and enhanced gravitational lensing techniques. Collaborations across observatories, combining JWST, Hubble, Planck, and future missions like the Euclid Telescope and the Nancy Grace Roman Space Telescope, aim to cross-verify findings. Despite the growing complexity, this era is often referred to as a golden age of cosmology. The tools, data, and questions now at our disposal are driving science to the edge of discovery. Yet, for all our advances, we remain humbled by the mysteries of dark matter, dark energy, and the very fabric of spacetime. Ultimately, the growing evidence of discrepancies, particularly the Hubble tension, may guide us to a deeper, more complete theory of the universe. Whether this means discovering new particles, refining our understanding of gravity, or even revolutionizing physics itself, the pursuit continues. What was once considered settled is now an open question. And in that uncertainty lies the thrill of exploration, the possibility that we are on the verge of uncovering a profound new layer of reality. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate at different stages of the universe's history. To solve these mysteries, astronomers will need both tools for advanced observation, like the James Webb Space Telescope, and theoretical frameworks capable of incorporating new data without discarding the successes of current models. The effects of JWST's discoveries extend far beyond cosmology, touching broader astrophysical questions, including the origins of life and the conditions required for life on other planets. By investigating faraway galaxies, astronomers hope to gain insight into how Earth-like planets might form around other stars, offering clues about the prevalence and diversity of life across the cosmos. Looking ahead, the James Webb Space Telescope promises to push the boundaries of our understanding of the universe. With its unprecedented sensitivity and resolution, astronomers will be able to map galaxies in greater depth, investigate exoplanet atmospheres, and explore the very beginnings of cosmic history with unparalleled precision. JWST's ongoing mission is set to continue revolutionizing our comprehension of astronomy, physics, and our place in the cosmos. Whether uncovering the mysteries of dark matter and dark energy, comprehending the formation of galaxies, or pursuing extraterrestrial life, the telescope is poised to transform our view of the universe in ways once considered impossible. In conclusion, the intersection of cutting-edge technology, conceptualization, precision, and observational innovation heralds the beginning of a new era in cosmology and astrophysics. JWST's contributions will help us improve our understanding of the universe's origins, challenge established theories, and open doors to groundbreaking discoveries. As we continue our journey of exploration, the universe's mysteries await, and with JWST leading the way, we are poised to uncover the secrets of our cosmic future. The legacy of the James Webb Space Telescope offers more than just precise measurements of the expansion of the universe and detailed observations of early galaxies. It is positioned to tackle some of cosmology's deepest questions. While the idea that our understanding of the world could be fundamentally faulty is nothing new, JWST's precision has sharpened this possibility. Central to the universe's structure are dark matter and dark energy, which remain poorly understood. JWST's ability to study the early universe and observe galaxies that formed just 300 million years after the Big Bang has provided unprecedented insights into galaxy formation. These observations challenge the established theory that galaxies should have taken longer to form, suggesting that processes like star formation and black hole growth may have been more efficient in the early universe. In addition, JWST's observations are contributing to the advancement of the study of dark matter, an elusive substance thought to play a critical role in shaping the universe's structure through its gravitational effects. JWST's insights may help us comprehend how dark matter affected galaxy formation and possibly reveal new characteristics of this mysterious substance. Beyond dark matter, JWST is also assisting in the study of conditions on exoplanets that could allow life to thrive on other worlds. One of the telescope's main objectives is to analyze exoplanet atmospheres, looking for signs of habitability or even life. By investigating the chemical makeup of these atmospheres, scientists hope to determine the conditions that might support life elsewhere in the universe. This could offer insights into how common Earth-like environments may be. As JWST continues to analyze data, it becomes increasingly apparent that we are on the brink of discovering new physics. Whether unraveling the nature of dark energy, exploring the unexpected complexity of early galaxies, or studying how dark matter behaves, JWST is opening new avenues for understanding the universe. It is not just refining our current theories, it is putting them under pressure, forcing scientists to rethink fundamental assumptions and explore new possibilities. These discoveries are testing the limits of physics, astronomy, and even philosophy as we deepen our understanding of the laws that govern our reality. As we continue to study the universe through JWST's lens, we are not merely learning about distant stars and galaxies, we are gaining profound insights into the very nature of the cosmos. The questions raised by JWST's findings could lead to a paradigm shift in how we understand the origin, structure, and future of the universe. Using the James Webb Space Telescope as a lens, the potential for a paradigm shift in our understanding of the universe grows increasingly likely. The unprecedented capabilities of the telescope have already provided an abundance of information that challenges many of our established assumptions about the cosmos. For example, the discovery of massive early galaxies forming just 300 million years after the Big Bang raises significant questions about the timescale and processes involved in galaxy formation. These galaxies appear far more mature than predicted, implying that processes like star formation and black hole growth may have occurred much faster and more efficiently than previously imagined. This discovery has sparked considerable discussion in the scientific community about whether our current models for the evolution of cosmic structures and galaxies need to be updated. In addition, the study of the early universe has revealed more complexities in the interactions between matter, and dark energy. The telescope's infrared capabilities allow it to peer deeper into the cosmos, observing events that took place within the first few hundred million years after the Big Bang, a period that was previously beyond our observational reach. These observations are crucial for understanding the role of dark matter, which makes up about 25% of the universe's mass but remains one of the most elusive components of the cosmos. While dark matter doesn't emit light and can only be detected through its gravitational effects, JWST's precision may help clarify how dark matter influenced the formation of galaxies and cosmic scale structures. This is an essential step toward understanding how our universe took shape and how it continues to evolve. A new frontier in the search for life. In addition to the ongoing quest to understand the fundamental components of the universe, dark matter, dark energy, and galaxy formation, JWST's observations are also offering exciting new possibilities in the search for life. One of the telescope's key missions is to study the atmospheres of exoplanets, searching for signs of habitability. By analyzing the chemical composition of these exoplanet atmospheres, scientists hope to detect the presence of molecules such as oxygen, methane, and carbon dioxide, which could be indicators of life. JWST's ability to observe exoplanets more closely and with higher sensitivity than ever before could bring us one step closer to answering the profound question: are we the only ones in the universe? JWST's contribution to this field extends beyond merely identifying potentially habitable exoplanets. It also promises to help us understand the environmental conditions that could support life. This includes studying the climate and atmospheric conditions of distant planets and learning how these factors could affect the possibility of life emerging.